Okay, thank you for the intro. I just want to mention I'm presenting on behalf of also Noel Soriano, who's also in the room, and Aaron Cordes up in the front. So just to share our motivation for this work, as we heard this morning, manure management's responsible for about a third of the carbon footprint of U.S. dairy production, well, the cradle to farm gate carbon footprint anyway. And what's really increased in the past couple decades has been manure storage methane emissions. So this category, compared with some of the other major categories like manure storage, N2O, and enteric methane, has been one of the primary drivers of increases in absolute emissions in the past several decades. And that's primarily driven by increasing use of liquid or slurry manure storages, as we just heard from Jason's presentation. So that's created some interest in how we can actually quantify manure methane emissions. As we heard again from Jason, the models are not perfect. So the models are oftentimes failing to capture some of the variation from farm to farm. This figure is showing modeled in black and then in gray what's actually measured in field in this one report. So as it shows in those two arrows, liquid and slurry might be among the most problematic or most variable relative to the model. And then by contrast, on-farm measurement is sometimes impractical and it can be difficult to separate out the sources. So there's been some recent developments of modeling and measurement combined approaches that would include studies that are combining some type of lab work with farm metadata to try and estimate the yearly emissions at farm scale. So two examples recently were Anderson et al., or Dan Anderson, their paper in 2015, and then some other work by a group in Denmark in 2024 with slightly different approaches. They found that the methane emission rate differed by season and with different ages of manure. And then more recently, it was showed that methane emission rate parameters differed for different types of slurry. So maybe just expected things to find. So I'm going to share what we, or how we approach this. We wanted to apply, oh, okay, we're good. We wanted to apply the same 3-day assay developed by Dan Anderson's group here to liquid dairy manure since it had previously been tested for swine deep pit manure. More specifically, we wanted to compare methane emission rates across these different factors: bedding type, manure type, storage type, typical storage duration and season, and then also examine the variance in methane emission rates attributable to site and storage within site. So in general, what we were expecting to find was that these methane emission rates would be greater for longer term stored manure. In warmer seasons, we'd have greater methane emissions and with organic bedding. And we also expected that we'd see substantial farm-to-farm variability. So how we actually did this was to have a year-long study with 27 different participating conventional dairies in Minnesota and Wisconsin. We sampled those farms across 2024. They represented various different types of bedding, about a third each for those different bedding types shown on the screen. Ooh, now it went twice. So we collected from each farm about a half-gallon sample of various different types of manure. So any type of liquid or slurry manure on the farm we collected. And the chemical composition was reported separately, so please check out Noel's proceedings. Each site was sampled 2 to 4 times in 2024, so we had a total of 208 samples, and we mostly had a pretty good distribution across seasons. So this is showing the calendar year and all of our sites on the y-axis here, except that in winter we collected fewer samples because storages were frozen. Then we took these samples and did a methane emission rate assay. So after collecting samples, took them back to campus, incubated them at 22 degrees C, or roughly room temperature, but in a controlled setting for 3 days. Then analyzed the gas amount and composition in the headspace. And then end goal is to predict yearly methane emissions from the manure storage in combination with methane or farm metadata. I'm going to share the results per liter of manure today. Just to compare this quickly with the biochemical methane potential test, which might be more familiar. So we're incubating at 22C for 3 to 7 days, more specifically 3 days for our assay, not using any inoculum, and we're always using a fresh sample. So really we're getting an instantaneous rate of methane emissions, not the cumulative total potential. Okay, there it went. To analyze this statistically, we modeled the log methane emission rate. We had fixed effects for all of the categories that I mentioned earlier in our objectives. And then we included random effects, random intercepts for site, or for each farm. So to go through kind of what we found here, overall, we had a skewed distribution of methane emission rates. So we had a lot of near zero values, and then also some very extremely high values. The median was 21.2 mils of methane per liter of manure per day. And then when we looked across these different factors, this shows bedding in the top panel and then manure type in the bottom panel here. So we had similar methane emission rates across different types of bedding and across different types of manure. We didn't have perfect balance across these categories, so we had some categories a bit overrepresented, but no apparent differences here. And then also similar methane emission rates across storage types and typical storage durations, surprisingly here. You can kind of see exactly what we found, but again, a lot of variability from sample to sample. Where we did see differences was across seasons. So this shows the seasonal differences in methane emission rate. And what we observed here was that fall had a greater methane emission rate, which was driven by both greater biogas production and then an increase in the methane concentrations in the headspace. So both of those factors led to a greater methane emission rate in fall versus other seasons. So then as our second objective here, we wanted to look at variance attributable to site or to farm, you might call it. I'm going to share for our 27 dairy sites in the x-axis what the methane emission rate was for all of the samples at that site. And what we found here was that there was large site-to-site variation. So you can see our lowest farm is very small, almost near zero. Then we had farms that kind of increased the spread and also increased the methane emission rate overall. So when we tried to quantify this, we had an intra-site correlation coefficient of 0.16. So about 16% of the variance after controlling for the fixed effects was explained by site. So in conclusion, or some of our main takeaways here, to get back to what we expected to find, we had no differences for longer term versus short term storage. So that contrasts our hypothesis. We found, we confirmed that emissions were greater in fall, no differences due to bedding type, and then we also confirmed our expectation that we'd have high variability from farm to farm. So just to get into a little bit of how we've started to discuss this, so the lack of differences by bedding type, manure type, storage type, and typical storage duration, wanted to point out that we're dealing with dairy farms that have a lot of differences in manure handling systems compared with maybe the swine farms that were included in this Anderson paper. And we also expressed our methane emission rates per liter of manure. Subsequently, we've also looked into it per kilo of volatile solids too, and don't seem to have differences there either. So there are some prior reports contrasting this, and then of course the IPCC Tier 2 approach would suggest that we'd have lower emission rates with shorter term storage, and that if we had more volatile solids, we would have more emissions, but of course maybe it's not all volatile solids are the same type of message here. So showing our greater methane emission rates in fall in a different way, this is across the calendar year. All of the methane emission rates we observed. Interestingly, we were conducting each of these assays at 22 degrees C, a fixed temperature, so it's not a temperature effect that we're observing. So this could indicate differences in substrate availability or activity of methanogens. And there's been mixed prior reports on this. There's been a report of methane emission rates with advancing depth in swine manure. And then volatile fatty acid concentration, so getting at that substrate availability question, there have also been kind of mixed reports there of um, whether VFA concentrations in manure might increase or decrease depending on when the storage is emptied and what else is going on. So I think that's still an open question. And then with respect to our site-to-site variability, this might relate to some other site-specific conditions that we haven't measured yet, or unrelated or unmeasured management factors. So what was shown in this Anderson paper with swine, 3 different swine farms, was that the highest farm was 1.75 times the lowest farm and methane emission rates on average. So it seems there might just be, even across for dairy and for swine, from farm to farm, there's something unmeasured that's causing some differences in methane emission rates. So in future work, we'd like to look into other site and manure storage metadata. We have some of this, but haven't analyzed it yet for manure removal frequency, storage volume, surface area of the storage, and then surface temperatures. We'd also like to relate methane emission rates to other manure constituents related either on the substrate end or else maybe on the fermentation end products side. So that could even trace all the way back to, I think, the diet characteristics from farms. But I think we should have time for questions, and thanks again.